Curing agents for epoxy adhesives: aliphatic amine, polyamide, and amidoamine. Curing agents: chemistry, mechanisms, and applications. Epoxy resins represent one of the most widely used classes of thermosetting polymers in structural adhesives, coatings, composites, and electronic materials. Their popularity arises from their excellent adhesion, chemical resistance, mechanical strength, and versatility in formulation. However, the inherent properties of epoxy resins depend strongly on the curing agents used to convert the liquid or low molecular weight oligomer into a rigid, cross-linked thermoset network. The curing process involves chemical reactions between the epoxy groups of the resin and reactive species present in the hardener or catalyst. These reactions generate a three-dimensional polymer network that ultimately determines the mechanical, thermal, and chemical performance of the final adhesive. In epoxy adhesive formulations, curing agents typically react with the epoxy functional group or with hydroxyl groups generated during the curing reaction. Alternatively, catalysts can initiate homopolymerization of epoxy groups without the direct incorporation of the catalyst into the polymer network. The curing agent, therefore, determines not only the reaction mechanism but also the resulting cross-link density and the types of chemical bonds formed within the cured polymer. A wide range of curing agents has been developed to tailor epoxy properties for specific applications. These curing agents can generally be classified into 6 main groups: aliphatic amines and modified aliphatic amines, polyamides, aromatic amines and modified aromatic amines, anhydrides, catalytic or latent hardeners, and polysulfides or mercaptans. Each class provides distinctive curing characteristics, including differences in curing temperature, reactivity, flexibility, and resistance to environmental factors. The selection of an appropriate curing agent depends on both processing requirements and final performance specifications. Processing considerations include viscosity, pot life, curing temperature, mix ratio, and application method. End-use performance criteria typically involve mechanical strength, toughness, thermal resistance, and chemical stability. Because curing agents strongly influence the structure of the cross-linked polymer network, they are a central component in the design of high-performance epoxy adhesive systems. Epoxy curing chemistry and the role of adducts. In many epoxy systems, curing agents are chemically modified before incorporation into adhesive formulations. One common strategy is the formation of epoxy amine adducts, produced by partially reacting an amine with an epoxy compound. These adducts provide several advantages in practical formulations. First, the formation of adducts reduces the vapor pressure of the curing agent, thereby minimizing volatilization during processing and decreasing exposure hazards. Second, adducts modify the reactivity of the curing system, allowing formulators to control the curing rate and pot life more effectively. Third, adduct formation can improve mixing ratios by bringing the stoichiometric proportions of resin and curing agent closer to equal volumes, which simplifies handling in two-component adhesive systems. Finally, adducts often introduce greater molecular flexibility into the polymer network, resulting in improved toughness and resistance to mechanical stress. The curing agent also plays a critical role in determining the final network structure of the epoxy thermoset. By influencing both the number of reactive sites and the reaction mechanism, the curing agent dictates the degree of cross-linking within the polymer matrix. A higher cross-link density generally increases stiffness, heat resistance, and chemical stability, but may reduce toughness and flexibility. Conversely, curing agents that introduce longer molecular segments between cross-links tend to produce more flexible materials with improved impact resistance. Flexibility in epoxy systems can also be enhanced by adjusting the stoichiometric ratio of resin to curing agent. For instance, changing the curing agent from a rigid anhydride such as hexahydrophthalic anhydride to a more flexible amine-based curing agent can significantly improve the impact resistance and elongation at break of the resulting polymer. Aliphatic amine curing agents. Classification and functionality. Aliphatic amines constitute one of the most important classes of curing agents for epoxy adhesives. These compounds contain nitrogen atoms with reactive hydrogen atoms that can participate in nucleophilic reactions with epoxy groups. Depending on the number of amine groups present, they may be classified as monoamines, diamines, triamines, or polyamines. Their molecular structures can be linear, branched, or contain cyclic components. A particularly useful method for classifying amines is based on their functionality, which refers to the number of reactive hydrogen atoms attached to nitrogen atoms in the molecule. The presence of multiple reactive sites enables the formation of cross-linked networks during epoxy curing. Amines are commonly divided into three categories. Primary amines, which contain two hydrogen atoms attached to each nitrogen atom. Secondary amines, which contain one hydrogen atom attached to each nitrogen atom. Tertiary amines, which contain no hydrogen atoms bonded to nitrogen. Primary and secondary amines react directly with epoxy groups, whereas tertiary amines generally act as catalysts for epoxy homopolymerization or as accelerators for other curing reactions. Many widely used epoxy curing agents belong to the primary amine category. Examples include diethylene triamine, DETA, triethylene tetramine, TETA, aminoethylpiperazine, AEP, diethylamine-propylamine, DEAPA, M-phenylenediamine, MPDA, and diaminodiphenyl sulfone, DDS. These compounds are capable of curing epoxy resins at room temperature or under moderate heating conditions. Primary and secondary aliphatic amines. Primary and secondary aliphatic amines were among the earliest curing agents developed for epoxy resins. Their widespread use stems from their ability to react rapidly with epoxy groups at ambient temperature, forming highly cross-linked thermoset networks. In this reaction, the amine nitrogen attacks the electrophilic carbon atom of the epoxy ring, resulting in ring opening and formation of a hydroxyl group. This reaction creates a secondary or tertiary amine linkage within the polymer network. The hydroxyl groups generated during the reaction can further accelerate the curing process. These groups facilitate additional reactions between epoxy groups and amines, as well as secondary reactions between hydroxyl groups and epoxides. The result is a complex cross-linking mechanism that gradually builds a three-dimensional polymer structure. Epoxy systems cured with aliphatic amines typically exhibit good resistance to moisture and solvents. They also demonstrate moderate thermal resistance, with heat distortion temperatures generally ranging from 70 degrees Celsius to 110 degrees Celsius. Short-term exposure of adhesive joints to temperatures approaching 100 degrees Celsius is often possible without severe degradation. Elevated temperature curing can improve the properties of aliphatic amine-cured epoxies. Higher curing temperatures promote greater cross-link density, which enhances mechanical strength, chemical resistance, and high-temperature stability. Limitations of aliphatic amines. Despite their advantages, aliphatic amines also present several challenges in adhesive formulations. One common issue is the formation of surface blushing, an oily layer that can appear under humid conditions. This phenomenon results from reactions between amine hydrogens and carbon dioxide in the atmosphere. Another problem arises from the high reactivity of these curing agents. Rapid reactions at room temperature can lead to short pot lives, limiting the working time available for mixing and applying the adhesive. The high cross-link density produced by these reactions may also result in brittle materials with limited impact resistance. Additionally, curing reactions involving large volumes of adhesive can generate significant exothermic heat. In thick sections, this heat buildup may lead to thermal degradation of the resin. As a result, batch sizes and bond line thicknesses must often be controlled to avoid excessive temperature rise. Common aliphatic amine curing agents. Diethylene triamine and triethylene tetramine. Diethylene triamine, DETA, and triethylene tetramine, TETA, are widely used polyamine curing agents for diglycid ether of bisphenol A, DGEBA, epoxy resins. Both compounds are highly reactive, low-viscosity liquids capable of curing epoxy systems at room temperature. Typical stoichiometric concentrations for these curing agents are approximately 10 to 11 parts per 100 resin, pph, for DETA and about 14 pph for TETA. However, formulations often use slightly lower concentrations, around 70 to 75% of the stoichiometric value, to improve toughness and extend pot life. Adhesive systems based on these curing agents usually have pot lives of about 20 to 30 minutes at room temperature. Complete curing may require several days at ambient temperature or can be accelerated by heating to approximately 100 degrees Celsius for about 1 hour. Although DETA and TETA-cured epoxies exhibit good general mechanical and chemical resistance, their performance declines at temperatures above approximately 50 degrees Celsius. For applications requiring greater thermal stability, aromatic amine curing agents are often preferred. Diethylamine-propylamine. Diethylamine-propylamine, DEAPA, is another aliphatic polyamine used in epoxy curing. This compound contains both primary and tertiary amine groups, allowing it to function simultaneously as a cross-linking agent and a catalyst. Compared with DETA or TETA, DEAPA produces systems with longer pot lives, typically several hours at room temperature, and lower exothermic heat generation. However, curing reactions proceed more slowly and often require elevated temperatures to achieve full conversion. Epoxies cured with DEAPA generally have lower cross-link densities than those cured with DETA or TETA. As a result, they exhibit reduced heat and chemical resistance but improved toughness and peel strength. Cycloaliphatic amines. Cycloaliphatic amines represent another important group of curing agents. These compounds provide good adhesion, excellent chemical resistance, and stable color characteristics. They are capable of curing epoxy resins at relatively low temperatures and even under humid conditions. When cured at elevated temperatures, cycloaliphatic amines can produce materials with high glass transition temperatures and strong mechanical properties. However, unmodified systems often exhibit brittleness and poor impact resistance. A notable example is aminoethyl piperazine, AEP, which contains primary, secondary, and tertiary amine groups. Epoxy resins cured with AEP show significantly improved impact strength compared with those cured with DETA or TETA. Modified aliphatic amines. Unmodified aliphatic amines have several disadvantages, including strong odor, skin and respiratory irritation, short pot life, and rigid cured products. These issues have led to the development of modified amine curing agents. One approach involves reducing the number of reactive hydrogen atoms through chemical modification. Amines can be reacted with mono or polyfunctional glycidyl compounds to form higher molecular weight adducts. These adducts typically exhibit lower volatility, reduced toxicity, and more convenient mixing ratios. Because the modified molecules contain longer chain segments between reactive sites, the resulting epoxy networks are generally more flexible and tougher. However, this improvement in toughness often comes at the cost of lower cross-link density and reduced thermal resistance. Glycidyl adducts. Glycidyl adducts of aliphatic amines are commonly prepared by partially reacting an amine with an epoxy resin. For example, diethylene triamine can be reacted with a DGEBA resin to produce a low-volatility curing agent with moderate viscosity. After the reaction, excess amine is removed by vacuum distillation. These adducts exhibit faster curing behavior because the amine is already partially reacted with epoxy groups. The presence of hydroxyl groups formed during the adduct preparation also accelerates further curing reactions. Ethylene and propylene oxide adducts. Polyamines can also react with ethylene oxide or propylene oxide to produce hydroxyalkyl derivatives. As the reaction progresses, the number of active hydrogen atoms decreases, reducing the reactivity of the curing agent. These derivatives generally exhibit lower skin irritation and lower viscosity. However, the reduction in reactive sites can lead to slower curing and somewhat diminished mechanical properties. In some cases, curing rates can be increased by adding acidic accelerators such as bisphenol A. Polyamide and amidoamine curing agents. Among the most commonly used curing agents for general-purpose epoxy adhesives are polyamides and amidoamines. These materials are widely used in two-component epoxy adhesives sold for construction, maintenance, and household applications. Both types of curing agents are derived from reactions between aliphatic amines and fatty acids. They offer several practical advantages compared with other curing systems. First, their mixing ratios are relatively non-critical, allowing formulations to tolerate variations in the resin to hardener ratio. Second, their lower volatility reduces odor and skin irritation. Third, they introduce moderate flexibility into the cured polymer network. Polyamide curing agents. Polyamide curing agents are produced by reacting dimerized fatty acids with polyamines such as diethylene triamine. The resulting molecules contain long hydrocarbon segments between amine groups, which increase flexibility in the cured epoxy network. Because of their high molecular weight, polyamides have relatively low vapor pressures and reduced toxicity compared with simple polyamines. They typically cure epoxy resins at room temperature and exhibit long pot lives with relatively low exothermic heat generation. However, the presence of long flexible chains reduces cross-link density. As a result, polyamide-cured epoxies generally have lower heat resistance and mechanical strength than systems cured with smaller amines. Structural performance often declines rapidly at temperatures above about 65 degrees Celsius. Despite these limitations, polyamides provide excellent adhesion and moisture resistance, making them useful in many construction and assembly applications. Amidoamine curing agents. Amidoamines are closely related to polyamides but contain only one amide group per molecule. Consequently, they have lower molecular weight, lower viscosity, and somewhat reduced functionality compared with polyamides. Like polyamides, amidoamines exhibit forgiving mixing ratios and allow significant variation in resin to hardener proportions. The properties of the cured epoxy can therefore be adjusted by modifying the formulation. Amidoamine cured epoxies display excellent adhesion, particularly to porous materials such as wood and concrete. They also cure effectively under humid conditions and are less corrosive than many aliphatic amines. In some formulations, high reaction temperatures are used to convert amidoamine structures into cyclic imidazolene derivatives. This transformation reduces viscosity and improves handling characteristics by decreasing the concentration of polar amide groups. Influence of curing conditions on epoxy properties. The final properties of epoxy adhesives depend not only on the curing agent but also on the curing conditions. Temperature, time, and stoichiometry all influence the extent of cross-linking within the polymer network. Higher curing temperatures typically accelerate reaction rates and increase cross-link density, resulting in improved thermal and mechanical performance. However, excessive heat generation during curing may lead to defects or degradation in thick adhesive layers. Stoichiometric balance between epoxy groups and reactive amine hydrogens is also critical. Deviations from the optimal ratio can reduce cross-link density, leaving unreacted functional groups that weaken the material. Because epoxy curing involves multiple competing reactions, including amine addition, hydroxyl epoxy reactions, and catalytic homopolymerization, the overall process is chemically complex. Achieving consistent performance requires careful control of curing conditions and precise formulation of the adhesive components. Conclusion. Curing agents play a central role in determining the performance characteristics of epoxy adhesive systems. By reacting with epoxy functional groups or catalyzing their polymerization, these compounds convert liquid resins into highly cross-linked thermoset materials. The structure and functionality of the curing agent influence the reaction mechanism, cross-link density, and ultimate properties of the cured polymer. Aliphatic amines remain among the most widely used curing agents due to their high reactivity and ability to cure epoxy resins at room temperature. However, their limitations, such as short pot life, odor, and brittleness, have led to the development of modified amine systems and alternative curing agents. Polyamides and amidoamines, derived from fatty acids and polyamines, offer improved handling characteristics and moderate flexibility, making them popular in general-purpose adhesive formulations. Through careful selection of curing agents and optimization of curing conditions, epoxy adhesives can be tailored to meet a wide range of industrial requirements. Understanding the chemistry and mechanisms of epoxy curing is therefore essential for designing high-performance materials for structural bonding, coatings, electronics, and advanced composite applications.